Hi, welcome to Sunil Maths tutorial, functional analysis class number 40. In this video, we learn three problems. Let us see the first problem. If capital S is a non-empty subspace of a Hilbert space capital H, then show that S perpendicular is equals to S triple perpendicular. So let us solve this problem. Here H is a Hilbert space and capital S is non-empty, and as well as S is non-empty and S is a subspace of Hilbert space. S is a subspace of capital H. We have to show that S perpendicular is equals to S triple perpendicular. Already we know that the few properties of the S perpendicular. The first property is S is always subset to S double perpendicular, and the second property is if S is subset to another set capital T implies as T perpendicular is subset to S perpendicular. It is subset or equivalent to here in both the cases. So right, we know the properties. S is subset or equivalent to S double perpendicular. If S is subset to T, then T perpendicular is subset to S perpendicular. So right, now by applying these conditions, S subset or equivalent to S double perpendicular implies as S double perpendicular whole perpendicular is subset to S perpendicular, this property, second one, which implies as S triple perpendicular is subset to S perpendicular. Let it be equation number 1. Again, S perpendicular is subset to S perpendicular whole double perpendicular, the first property, which implies S perpendicular is subset to S triple perpendicular, equation number 2. Combining equations 1 and 2. Now combining equations 1 and 2. From equations 1 and 2, we conclude that S perpendicular is equals to S triple perpendicular. Again, you remember that this is a simple property, depends upon these two basic properties. S subset to S double perpendicular. If S subset to T, then T perpendicular is subset to S perpendicular. That's it. Now we solve one more problem. This one, S perpendicular is subset to S triple perpendicular, is important for 5 mark section. Let us see the second one. Here, if capital M is a linear subspace of a Hilbert space capital H, then show that M is closed, implies and implied by M is equals to M double perpendicular. Right. We prove this. Excuse me. Let capital M is a linear subspace of a Hilbert space capital H. In the introduction part, this H is a Hilbert space. And capital M is a linear subspace. Of capital H. We have to prove that this M is closed. Implies and implied by M is equals to M double perpendicular. So in the first part, suppose M is closed. Suppose M is closed. Closed means it is closed subspace of Hilbert space. It means capital M is closed linear subspace of capital H. If M is closed linear subspace, then M perpendicular is also closed linear subspace of capital H. By previous theorem we know that H is direct sum of M and its M perpendicular. H is direct sum of M and its perpendicular. So let it be equation number 1. Again, M perpendicular is closed subspace. M perpendicular is closed subspace of H. Closed subspace of H. So M perpendicular, whole perpendicular is also closed subspace of H. It means M double perpendicular is also closed subspace of H. If M double perpendicular is closed subspace of H, again then by previous theorem, H can be written as direct sum of M perpendicular and its M double perpendicular. Equation number 2. Now combining equations 1 and 2, you see here, in equation 1 H is equals to M perpendicular direct sum M. Here M perpendicular direct sum M double perpendicular. So equation 1 and 2, I mean both equation 1 2 represents as H is direct sum of different sets M perpendicular and M perpendicular M double perpendicular. It follows that then we conclude that here it is only possible if M is equals to M double perpendicular. That's it. Let us see the converse part. In the converse part we assume that suppose M is equals to M double perpendicular. Now here you clearly observe that M double perpendicular can be written as M perpendicular whole perpendicular, which is a closed subspace of capital H. And this M double perpendicular is equivalent to M, and M double perpendicular is closed. So obviously this M is also closed subspace. M is also closed subspace of capital H. That's it. From this we conclude that M is closed implies and implied by M is equals to M double perpendicular. One of the very important question for 5 mark section and one of the important property in Hilbert spaces. Let us see the question number 3. Here, if S is a non-empty subset of a Hilbert space capital H, then show that the set of all linear combinations of vectors in capital S is dense in capital H, implies and implied by S perpendicular is equals to Z0. So, one of the important property of Hilbert spaces, and also right, let us prove this. Here in the introduction part, H is a Hilbert space and S is a non-empty subset of S. S is non-empty and S is subset to capital H Hilbert space. Now define a set box S. Define box S. It is the set of all linear combinations of vectors of capital S. Remember this definition. Box S is equals to set of all linear combinations of vectors of S. Now we have to show that this S is a dense in H. Our aim is we have to prove that this box S is dense in H, implies and implied by S perpendicular is equals to set 0. So right. So in the first part we assume that suppose box S is dense in H, then obviously box S bar is equals to H. Box S bar is equals to H. Remember this property? Capital A is dense in X, capital X, implies and implied by A closure is equals to X. A is dense in full space capital X, implies and implied by closure of A is equals to full space capital X. So here also we assume that yes, box S is a dense set in capital H. So box S bar is equals to capital H. What it means? You have to understand here. Box S bar is equals to H means every point of H is a point of box S bar, is a point of box S bar. So right, remember that. First we show that if x perpendicular to m is subset of H, then x perpendicular to m bar also. So we are going to prove this condition. If x is perpendicular to m, where m is a subset of H, then this x is perpendicular to m bar also. So right, now define if z is a limit point of m, implies there exists a sequence Zn in capital M such that the sequence Zn converges to Z as n tends to infinity. We take Z is a limit point of M. By applying this definition, there must be a sequence Zn in the set capital M converges to Z as n tends to infinity. So Zn belongs to capital M and x is perpendicular to M implies as x perpendicular to Zn for all n. It means inner product of x comma Zn is equals to 0. It means limit n tends to infinity, inner product of x comma Zn is equals to 0. It means inner product of x comma limit n tends to infinity Zn is equals to 0. Again implies as x comma z, inner product of x comma z is equals to 0, implies x is perpendicular to z. If x is perpendicular to z, then obviously x is perpendicular to m bar. So therefore x belongs to capital M implies as x belongs to m bar. Let it be equation number 1. Now we show that S perpendicular is set to set 0. Our main aim is to show that S perpendicular is equivalent to 0. So to prove this, take an element. Let us take x belongs to S perpendicular. Then obviously x is perpendicular to S. So obviously x is perpendicular to box S. So which implies as x is perpendicular to box S bar by previous calculation. So x is perpendicular, this is from equation 1. So obviously x belongs to capital H, which implies as x belongs to H perpendicular. If x belongs to H perpendicular, then this x is equals to 0 because box S bar is equals to H. X equal to 0. So what we show that x belongs to S perpendicular implies as this x is equals to 0. Therefore, S perpendicular consists only 0 element. So we assume that box S is dense in H. we prove that S perpendicular is equals to Z0. S perpendicular is equals to Z0. Right. We go for converse. Reverse part. In the reverse part, assume that S perpendicular is equals to 0. Let us assume that S perpendicular is equals to 0. Let us assume that S perpendicular is equals to Z0. We have to prove that box S bar is equals to H. That is, S is dense in H. S is dense in H. So if possible, to prove this, assume the contradiction point. If possible, let box S bar not equals to H. Box S bar not equals to H. Then there exists a vector. X belongs to capital H and X does not belongs to box S bar. Here we are assuming box S bar not equals to H. Box S bar is not equals to H means there must be an element in H which does not lies in box S bar. So right. So here what it means? Box S bar is a closed subspace of H. Closed subspace of H. If box S bar is closed subspace of H, then box S bar perpendicular is also closed subspace of H. Then by previous theorem, H can be written as box S plus box S perpendicular. Box S bar perpendicular. H can be written as sum of box S bar perpendicular. So therefore, an element X belongs to capital H implies as X is equals to Y plus Z, where this Y belongs to box S bar and Z belongs to box S bar perpendicular. We claim that Z is not equals to 0. We claim that Z not equals to 0. Suppose if Z is equals to 0, then this X equals to Y belongs to box S bar, which is a contradiction. To that X belongs to box S bar. So there exists a non-zero vector. Z belongs to box S bar perpendicular, satisfying the condition Z is perpendicular to box S bar, which implies that Z is perpendicular to box S, which implies that Z is perpendicular to S, which implies that Z belongs to S perpendicular. Thus Z is equals to 0 because S perpendicular consists only one vector, 0 vector here. We assume the same thing here. Here you observe that. We assume that S perpendicular is equals to 0. So obviously this element Z becomes 0, but this is a contradiction. This is a contradiction because of we assume that Z is a non-zero vector. Clearly Z is a non-zero vector. So this contradiction exists because of our assumption. Box S bar not equals to capital H. Box S bar not equals to capital H. Hence, our assumption H not equals to box S bar is wrong. If it is wrong, then what is right? H is equals to box S bar. If H is equals to box S bar, obviously this S is dense in H. Therefore, we conclude that S is dense in H implies and implied by S perpendicular is equals to Z0. It consists only one element. That's it. Keep learning. In the next video, we learn orthonormal set and properties of orthonormal set and examples of orthonormal set. That's it. Keep learning.